So now that we know how to use the state sparse bitset within the compact table algorithm, let's now look at how it is implemented. So state sparse bitset. There are bitsets. How do we implement bitsets? Well, bitsets on computers, they cannot be an infinite number of bits together. We have an upper bound. In fact, in Java, one of the longest structure is the long, integer long, where we can store 64 bits together. So we are going to use an array of long to allow us to store more than 64 bits together. And here in our example, we are going to use 4-bit long words because it's easier for you to understand. Okay, we have bitsets. And in our bitsets, each bit will be associated to one of the tuple, 0 if the tuple is not valid, 1 if the tuple is valid. Perfect. Now we have state sparse bitset. So we need a structure to be stateful. We can do that easily with state longs. These are long that are made stateful, so they can restore their state themselves. And so if we use an array of state long instead of an array of long, well, the array of state long will just restore itself easily. It's what we call data structure composition. We are composing one data structure with other data structure already there. Okay, but now can we make this a bit more optimized? So that's the sparse part. Okay. When you have bitwise AND operation, which is what we are going to do with the valid tuples, we are going to do intersection and AND operation. Well, there is one mathematical property that is good, is that if the bit set is empty and something, it will always result in empty. So do we need to compute the intersection or the AND if we know that part of the bit sets are empty? No. So what we can do is to avoid the computation of the words that are empty. And to do that, we will use a data structure that we already saw in the STR algorithm, which is the state sparse set. So not a bit set, a simple set. So recall the STR algorithm. We had this array of indexes for all the tuples. So here we have an array of the indexes in the word. And we have our stateful int that give us the number of elements in the table here in the array. And if one word becomes empty, we swap it with the last one, and we decrease here the size, and we now have our new set of non-empty words versus the empty words. And if we need to have a restoration, we just need to restore here the number, which will restore the separation between the two sets, and one will be again in the set of non-empty words. So easy. But can we do better? Yeah, we can still do better for the test of the intersection. So when we test, is there a bit that is between valid tuples and support? And we are going to do that with what we call a residue. The residue is the ID, the index of a given word, where the intersection was non-empty the last time we had to do an intersection. Why do we choose to keep it? Well, if we are in a search tree and we descend into a search tree, if there is a non-empty intersection in a given word, well, it's still likely that at the next intersection it will still be non-empty. So we want to try this word first. And if the word is not working, if this intersection is now empty, well, we will try a new word, a new residue to keep. So pseudocode is here. For for each support we have a residue. So when we try the intersection between the support and the valid tuple, we will first get back the last residue that we have, so the last word where support and valid tuple intersect themselves. We test the intersection between the two. If it's still non-empty, which what we hope is happening, then we know that the intersection is non-empty. And if not, we will iterate on each of the remaining non-empty words in valid tuples. So we will start at the one at the size, and we will check the ID of each of them. And we do the intersection, and if we find an intersection that is non-empty, we store the new residue for the given support that we are testing. So each of the support for each of the pair of variable value has its own residue, because it's not the same words that was the last that led to an intersection. And if after that we still didn't have found an intersection, that means there is no intersection. We can return false, and in that case we can remove the value. Okay, let's now look a bit at the API of the state sparse bitset and the bitset that we are using. They have the same API as the Java util bitset implementation. So for the bitset here, mask, it's a temporary bitset that we can use for computation. We can clear them, so empty the bitset. We can do OR operation to do the bitwise OR. And for the reversible sparse bitset, so the stateful sparse bitset, we have the AND, which can do the AND operation between the mask and the word, and the intersect, which will do the test is the intersection empty between the two. So how can we implement that in practice for the update and then the filtering? So first the update. So the update, we needed to do the previous value of valid tuples, bitwise AND, the union, so the bitwise OR between all the support for the remaining values. So first, we clear our temporary bitset. We add, well, we unionize this empty bitset with the support for the first variable, then for the second one, and the union between two sets is the bitwise OR. And then, so the mask contains now the value of this, and then we do the AND operation between the mask and valid tuples to update the value of valid tuples. For the filtering, is this value still possible? We use the intersect operation between the valid tuples and the corresponding support, and if this answer is false, because we do the negation, so not false is true, we remove the element. So we try to find an empty intersection. So to summarize the state sparse bitset, it's a set, so a collection of objects, in our case the tuples. It's a bitset, so it uses bits to store the object. If the bit is set to 0, the object is not there. If the bit is set to 1, the object is there. It's sparse. It means that we have optimized the data structure to avoid some part of the computation, so avoid the empty words and try to do the intersection the most efficient way possible. And it's a state data structure because it allows automatic restoration to a previous state. So now that you know all of this, you can implement compact table with everything.